Vibration analysis. Procedures for accurate evaluation of machinery condition. Part 2. Common problems. A group of problems that is common in many machines includes imbalance, bent shaft, soft foot, misalignment, looseness, resonance, rubs, problems that cause pulses, and oil whirl. Vibration analysis. Procedures for accurate evaluation of machinery condition. Common problems. Imbalance. Imbalance is a linear problem. If a rotor is out of balance, it should be out of balance by the same amount, through 360 degrees of rotation. Each cycle in the time domain signal will have the same amplitude and the time signal will be sinusoidal. The first 4 or 5 harmonics of rotating speed at low levels or about 0.05 inch per second are normally present in fluid film bearings. The following conditions cannot be present with pure imbalance. Number 1, noise skirts at the base of the fundamental. Number 2, half shaft or fractional shaft speed. Number 3, harmonics of speed in anti-friction bearings or high amplitude harmonics in fluid film bearings. Number 4, wide-banded noise. And number 5, any form of a beat or amplitude modulation. Figure 3 contains a frequency spectrum and time signal of imbalance. Figure 4 contains a frequency spectrum containing some of the above undesirable frequencies. Warning: if a rotor is out of balance and other problems are present, all other problems must be repaired before the unit is balanced. If you have ever tried to balance a rotor and did not succeed after 4 trial runs, you either made an error or you were trying to solve a vibration problem by balancing when imbalance was not the problem. If you have ever observed a rotor that has balance weights welded all around the rotor, you have observed many attempts to solve a vibration problem by balancing when imbalance was not the problem. Rotors with a vibration problem should not automatically be assumed to be out of balance. True imbalance can be diagnosed using this technology and some perseverance. Vibration analysis. Procedures for accurate evaluation of machinery condition. Common problems. Bent shaft. A bent shaft is a form of imbalance and balancing can reduce the vibration level. However, balancing cannot straighten the shaft. The bent shaft prevents adequate alignment in some cases and causes clearance problems in others, depending on where the bend occurs. The characteristic spectrum of a bent shaft is a distinctive second harmonic, as in Figure 5. If the shaft is bent enough to cause a misalignment problem, one of the indications of misalignment could also be present. If a shaft is bent, the end of the shaft will rotate in an orbit. When this occurs, a force vector will be felt on the coupled shaft through 360 degrees of rotation. This force produces a high amplitude signal at the fundamental speed, as in Figure 3. For example, if a motor has a bent shaft and is coupled to a pump, the time signal and frequency spectra could be similar to Figure 5. The second harmonic is distinctive and is in phase with the fundamental. The frequency spectra and time signal from the pump indicate imbalance. However, the problem is caused by the bent shaft on the motor. The time signal is a good sinusoid. This is true because the shaft is bent by the same amount through 360 degrees of rotation. The only distortion would be that caused by the coupling, looseness, etc. If the second harmonic is not in phase or is changing phase with the fundamental, the unit is loose, and the shaft may not be bent. Where the unit is operating above first critical, there is a 180 degrees phase shift in the residual imbalance. Since the imbalance is caused by the bend in the shaft, the truncation could move to the top of the time signal in some cases, and the second harmonic would be 180 degrees out of phase with the fundamental. The section on coast-down data provides more insight. When troubleshooting, data should be taken in the horizontal, vertical, and axial directions. A bent shaft on a motor that belt drives another unit could look like imbalance, as in Figure 3, or the second harmonic could be present, as in Figure 5. As a simple test, insert a wooden pencil in the center hole at the end of the shaft. If the pencil vibrates, the shaft is bent. The VCI Model 340 proximity probe can also be used to measure the total indicated runout or TIR of the shaft while the machine is running. Vibration analysis. Procedures for accurate evaluation of machinery condition. Common problems. Soft foot. Soft foot can generate a high-level fundamental or second harmonic. Soft foot can and often does indicate a misalignment problem. The best way to prove soft foot is to observe the vibration level while tightening or loosening the bolts on each foot. The vibration amplitude will increase or decrease significantly when pressure is applied to the bolts on the soft foot. The frequency spectrum and time signal can indicate imbalance, bent shaft, looseness, and/or misalignment, depending on how the rotor and casing are distorted by the soft foot. When a soft foot is present, the machine may have to be removed, reset, and realigned. Vibration analysis. Procedures for accurate evaluation of machinery condition. Common problems. Misalignment. Misalignment can occur in several places in rotating machinery. For example, misalignment can occur along the shaft centerline between bearings. Misalignment can also occur in meshing gears. However, misalignment more frequently occurs when two machines are coupled together. When misalignment occurs, the first three harmonics are generated. If coupling halves are misaligned, the first three harmonics of rotating speed are generated. If gears are misaligned, the first three harmonics of gear mesh frequency can be generated. For these reasons, solo data should be taken on all motors and turbines before they are coupled to the driven unit. If you want to know the type of misalignment, take data in the horizontal, vertical, and axial directions on the drive and off ends of the drive and driven units. If the first three harmonics are distinctive in 1. The horizontal direction, there is vertical offset misalignment. 2. The vertical direction, there is horizontal offset misalignment. 3. The axial direction, there is angular misalignment. And 4. All directions, there are horizontal offset, vertical offset, and angular misalignment. If the first three harmonics are distinctive, then misalignment is present, regardless of the amplitude within prescribed calibration levels. The problem is that most people think low amplitude levels indicate a good machine. This could be true in some situations, however, there are severe problems that can occur with low amplitudes. Misalignment is one of them. In the real world, most misalignment problems go undetected and unrepaired until the coupling, shaft fits, or the bearings are worn out. There are many types, combinations, and degrees of misalignment. The signals obtained can also vary with coupling type, shaft size, and speed. Because of these factors, a single example of misalignment is not adequate. However, this writer has observed several distinctive patterns associated with misalignment. Please remember various combinations of amplitude and phase can cause some signals to be very different. Figure 6 contains a spectrum and time signal of misalignment. Please note. Number 1, the first three harmonics of speed are distinctive. The amplitude relationships could vary significantly. If the amplitude of the second harmonic is higher than the first and third harmonics, the shaft may be bent. Number 2, the time signal contains a fast rise time on one side and two positive going peaks on the other side of each cycle. As the shafts rotate, the coupling bends and then frees up once each revolution. When the coupling is binding, the three peaks are generated. When the coupling frees up, the fast rise time is generated. Number 3, the time signal is normally truncated on the negative side because the signals are in phase. However, in some cases, the signals could be out of phase. Operating speeds above first critical is a good example. And number 4, the time period for each half revolution may not be equal. The unit speed decreases when the coupling is in a bind and increases when the coupling is free. The amplitudes of the first three harmonics can approach a 6 dB per octave slope, as in Figure 7, or a 12 dB per octave slope, as in Figure 8. The 6 dB per octave slope indicates a level of increased binding of the coupling. When the signals approach a 12 dB per octave slope, the amplitude may increase, the coupling may be locked and rigid, and severe wear and/or failure may occur relatively quickly. Vibration analysis. Procedures for accurate evaluation of machinery condition. Common problems. Looseness. Looseness can and does take many forms. The various forms are created by the type of looseness, that is the machine or rotating unit loose, the amount of looseness, and other associated problems such as imbalance, misalignment, defective bearings, etc. 1. Bearings loose on the shaft. 2. Bearings loose in the housing. 3. Common forms of looseness. 4. Noise. 5. Diagnosis of looseness. Vibration analysis. Procedures for accurate evaluation. Looseness. Bearings loose on the shaft. When a bearing is loose on the shaft, the type of signal generated depends upon how the unit is installed. If the inner race is turning on the shaft in an electric motor that is belt driving another unit, the frequency spectra may appear as imbalance with a high amplitude spectral line at motor speed, as in Figure 3. However, the time signal may be distorted in some manner. The time signal may vary in amplitude, be truncated, contain harmonics, contain a beat, or the time period may be different at each half cycle. Some of these characteristics may produce harmonics and other frequencies, such as the speed of the driven unit. On direct coupled units, if the bearing is turning on the shaft, the frequency spectra may contain a spectral line at unit speed and another spectral line a little lower than unit speed. The lower spectral line is the speed at which the inner race is turning. The difference frequency or delta F is equal to the unit speed or how fast the bearing is turning relative to the shaft, as in Figure 9. The time signal will contain a beat caused by the two frequencies going in and out of phase with each other. Vibration analysis. Procedures for accurate evaluation. Looseness. Bearings loose in the housing. When the fourth harmonic of rotor speed is distinctive, the bearing may be loose in the housing. The data in Figure 10 was taken from a motor running solo. Note the overall amplitude is only 0.1 inch per second, and a serious problem exists. The fourth harmonic is distinctive, and the second and third harmonics are present. These harmonics should not be visible with prescribed calibration levels. Caution should be used in diagnosing bearings that are loose in the housing when a pump has 4 vanes on the impeller because the fourth harmonic may be caused by vane pass frequency. Some press rolls may also contain the fourth harmonic of speed. This can occur when the roll has 4 high places. There are many more examples, that is screws that have 4 flights, etc. The only way to determine which problem exists is to look at the phase relationship between the fourth harmonic and the fundamental. If the fourth harmonic is out of phase or is changing phase, the bearing may be loose in the housing. If the fourth harmonic is in phase and maintains a constant phase relationship, the bearing may not be loose in the housing. Another indication that the bearing is loose on the shaft or loose in the housing is careful analysis of bearing frequencies, particularly ball pass frequencies of the outer and inner races. When calculating bearing frequencies, the rotating unit speed is used. The normal assumption is that the bearing is rotating at the same speed as the shaft, and the fixed race is not rotating. These assumptions are wrong in many cases. The bearing frequencies are actually determined by the relative speed between the inner and outer races. If either race is turning on the shaft or is loose in the housing, the bearing frequencies will be less than those calculated. Once again, care must be used because if the contact angle is increased, the ball pass frequency of the inner race will decrease. Careful analysis of bearing frequencies can identify bearings that are loose on the shaft or in the housing. Vibration analysis. Procedures for accurate evaluation. Looseness. Common forms of looseness. The more common forms of looseness could start with an increase in the amplitude of the fundamental and the harmonic content, as in Figure 11. Many unskilled analysts try to solve these problems by balancing. Such efforts may not be successful. As the looseness increases, the harmonic content also increases, and the amplitude of the fundamental and the overall RMS value can actually decrease. The next stage of looseness could be the appearance of spectral lines at fractional shaft speed. These spectral lines could occur at 1/2, 1/3, 1/4 shaft speed, etc., depending upon the type and amount of looseness. The author has observed 1/7 shaft speed when the spacer and outer race were switched on a cylindrical roller bearing. Fractional shaft speed is often generated when the rotor does something different every X revolution. One example is when the amplitude of every other revolution is higher, as in Figure 12. If an event such as a pulse is occurring every third revolution, then 1/3 shaft speed will be present. These events may not occur each and every revolution. However, they must occur several times during the averaging process to generate spectral lines at fractional shaft speed. The amplitudes of these spectral lines can be quite low because they may not be present in every time period. Vibration analysis. Procedures for accurate evaluation. Looseness. Noise. The last stage of looseness is often noise. The noise can be wide-banded white noise or narrow-banded pink noise. Noise contains all frequencies in a defined bandwidth. This machine is moving in an unpredictable manner and is generating all frequencies in the bandwidth, as in Figure 13. Severe looseness is the only problem that can generate such frequencies except for cavitation in pumps. When cavitation occurs, vein pass frequency is generated, and the spectral line at vein pass frequency is normally on top of wide-banded noise, as in Figure 41. Various operational parameters will verify the cavitation problem. Some machines fail before noise occurs. When noise occurs, the machine can and normally does fail in a short period of time. The time period could be hours, days, weeks, or months in some less severe cases, but not years. Vibration analysis. Procedures for accurate evaluation. Looseness. Diagnosis of looseness. The earlier a machine is diagnosed, the more precise and accurate is the diagnosis. The later the diagnosis is made, the more general and less accurate is the diagnosis. For example, early stages of looseness, misalignment, bearing defects, and gear problems can be accurately diagnosed. In the later stages, only wide-banded noise may be present, and the diagnosis may be looseness when, in fact, there are bent shaft, misalignment, and defective bearings present. This is why diagnostics of rotating machinery may not always identify all problems. Accurate diagnosis will always identify the most severe problem, which is often looseness. Vibration analysis. Procedures for accurate evaluation of machinery condition. Common problems. Resonance. Resonance is a very complex subject. It is beyond the scope of this book to provide all the mathematical descriptions. However, a practical explanation is provided. All things have one or more resonant frequencies. These frequencies are often called modes, that is first mode, second mode, etc., as explained in earliest chapter. Please find from the playlist of this video channel in section Vibration Analysis Introduction. Resonant frequencies are often called natural frequencies and critical speeds. Natural frequency may be a better term because it refers to the natural frequency at which the machine is inclined to vibrate. The term critical speed is used when a resonant/natural frequency equals the unit speed. When this occurs, the machine may have exceptionally high vibration levels. A resonant frequency is often referred to as though it were a single frequency. However, in actuality, a resonant frequency is often a band of frequencies. The bandwidth is determined by damping. A resonant frequency can be well damped, which means it will be low in amplitude and wide-banded. A resonant frequency can also be undamped. This means the amplitude will be high and it will be narrow-banded. The resonant frequency can be anywhere between well-damped and undamped. Resonant frequencies that are well-damped contain low vibration levels. Undamped resonant frequencies contain high vibration levels. A measure of how violent the resonance may be is called the amplification factor, which was discussed in earliest chapter. Please find from the playlist of this video channel in section Vibration Analysis Introduction. Natural frequencies can be determined in one of three ways. Number 1, the resonant frequency can be calculated or the resonance and deflection calculator program can be used. Since we live in an imperfect world, calculated frequencies may not be exact. However, they can be very close. Number 2, the resonant frequency can be determined with a bump test. Under this test, the machine or piece is bumped or hit, and the resonance is measured. For example, if you strike a crystal glass with a fork, it will ring or vibrate at its resonant frequency. The energy put into the glass by the fork excites the glass into vibrating at the resonant frequency. And number 3, if a machine is operating above the first critical speed, coast down and startup data can be used to identify the resonant frequency, bandwidth, and amplification factors. Coast down data can be taken only from machines that will coast. Startup data can only be used to identify resonance if the machine can be started slowly. As can be seen from the above list, all problems cannot be identified from bearing cap vibration while the machine is running. Special tests must be performed in some cases. These special tests are explained in the last section of this chapter. Vibration analysis. Procedures for accurate evaluation of machinery condition. Common problems. Rubs. Some people think of rubs as surface-to-surface contact over long time periods, causing much friction and heat. Some rubs can occur in this manner. The signal generated is wide-banded noise, and the result is a sudden and catastrophic failure. A more common form of rub is when the rotating unit hits something once or many times each revolution. When one hit occurs per revolution, a pulse is often generated. The reciprocal of the time period between the pulses is unit speed. A rub can also occur at a specific multiple of rotating speed. For example, if each blade on a motor cooling fan is hitting something, the frequency generated can be the number of blades on the fan times the speed of the fan. The spectral line at blade pass frequency can have plus and minus sidebands at unit speed, depending on the characteristics of the time signal. If the time signal contains pulses, amplitude, and/or frequency modulation, these sidebands will be present. A rub can also occur when the surface of the rotating unit hits another object a number of times each revolution. This type of rub can generate a series of spectral lines, and the difference frequency between the spectral lines will be equal to unit speed. The center frequency could be equal to the number of hits times speed, or an excited natural/resonant frequency. See Figure 14. If two series of spectral lines occur, then two resonant frequencies are being excited. Vibration analysis. Procedures for accurate evaluation of machinery condition. Common problems. Problem that cause pulses. A pulse is caused by a hit or an impact. Four measurable characteristics of a pulse are: 1. Repetition rate. 2. Amplitude. 3. Frequency. And 4. Width. The repetition rate identifies how often the pulse is occurring. The repetition rate is normally unit speed. When more than one pulse is occurring each revolution, the pulses can appear random in the time domain. However, the frequency spectrum will have a series of spectral lines, and the difference frequency will be unit speed. If two pulses are occurring each revolution, every other spectral line will be higher in amplitude, as in Figure 15. If four pulses are occurring each revolution, every fourth spectral line can be higher in amplitude, etc. Pulses can also occur at other generated frequencies, such as ball pass frequencies of the inner and outer races, or gear mesh, vane, and blade pass frequencies. Pulses can occur randomly. When random pulses occur, the frequency spectrum contains noise, the rotating unit is flopping and banging around in an unpredictable manner, and failure is imminent. Amplitude is affected by problem severity, resonance, damping, and loading. Pulse amplitude in the time domain can be very low or very high, depending on the aforementioned points. In the frequency domain, the spectral lines range from very low amplitude to non-visible because of the low energy or lack of energy between the pulses. For this reason, pulses are often overlooked if the time domain signal is not analyzed. If a pulse is suspected, data taken with an accelerometer often yields a more pronounced pulse. This is true because an accelerometer measures rate of change per time period, and pulses often have a fast rise time. A pulse can be empty, which can mean it does not contain a frequency. An empty pulse occurs when a natural frequency is not excited in amplitude, or the impact is measured. In this case, the fundamental in the frequency spectrum will be low or non-visible. The second, third, fourth, fifth, etc. harmonic can be higher in amplitude, as in Figure 16. When an impact excites a natural frequency, the pulse will contain the excited frequency, and a series of spectral lines will be around the excited frequency. Once again, the amplitude will be quite low if the signal is damped because there will be little or no energy between the pulses. When a pulse is empty, the pulse width will be narrow and only half a cycle wide. If a natural frequency is excited, the pulse width will be determined by the damping. Figure 17 contains a well-damped time signal and frequency spectrum. Figure 18 contains a relatively undamped time signal and frequency spectrum. Once the above pulse parameters have been identified, it may be difficult, in some cases, to identify the specific problem. This is true because more than one problem can cause a pulse at unit speed. Following are some examples. Number 1, when coupling halves are set too close together, they can hit once each revolution. Number 2, a broken, cracked, or chipped tooth on a gear. Number 3, a circumferential crack in a roll. And number 4, steam joints. Number 5, looseness in bearings. Number 6, a bearing with a cracked inner race. And number 7, loose head bolts, manhole covers, and siphons on rolls. Vibration analysis. Procedures for accurate evaluation of machinery condition. Common problems. Oil whirl. In some lightly loaded, plain journal bearings, a phenomenon called oil whirl can occur. This is caused when the rotating unit pushes up an oil wedge in front of the shaft. As the shaft tries to roll over the oil wedge, the shaft whirls around the bearing while rotating at a given speed. The general view is that oil whirl frequency varies between 40 to 50% of shaft speed. Oil whirl may not occur in tilted pad, pressure dam, and crush fit bearings. This writer agrees with these generally held views. However, additional information can be learned from the time domain signal and frequency domain spectrum. Figure 19 contains the time signal and frequency spectrum from an oil whirl problem. Turbine speed is 93 Hz, and oil whirl frequency is 43 Hz. In most machines that have oil whirl problems, a knocking noise can be heard. This noise is generated because the oil whirl does not occur continually. Rather, the shaft makes a few whirls, stops for a couple of revolutions, then makes a few more whirls. This intermittent whirling can sound like a knock. The time period between points 1 and 2 in figure 19 is 0.02325 seconds or 43 Hz, which is oil whirl. The time period between points 3 and 4 is 0.01075 seconds or 93 Hz, which is turbine speed. The time period between points 5 and 6 is 0.1428 seconds or 7 Hz. This is the frequency of maximum oil whirl amplitude. There is a spectral line at 50 Hz, which is 43 Hz plus 7 Hz. There is also a spectral line at 36 Hz, which is 43 Hz minus 7 Hz. The spectral line at turbine speed has plus and minus sidebands of 7 Hz, which are 100 Hz and 86 Hz. A spectral line is also located at 136 Hz or 43 Hz plus 93 Hz, which is the sum of oil whirl frequency and turbine speed. This frequency also has plus and minus sidebands of 7 Hz or 129 Hz and 143 Hz. Note: the spectral line at 50 Hz is a sideband or some frequency and is higher in amplitude than the discrete frequency at 43 Hz. A sideband cannot be higher than the discrete frequency, except when the sideband equals a resonant frequency or contains more energy than the discrete frequency. From the above empirical data, it would appear that oil whirl frequency is equal to turbine speed minus 7 divided by 2, or oil whirl frequency equal to speed turbine minus 7 divided by 2 equal to 93 minus 7 divided by 2 equal to 43. This formula meets the current description that oil whirl is somewhere between 40 and 50% of turbine speed. We recognize that some refinements to the formula may be required in the future. Thank you.